Hello, everybody. Good morning. Welcome. Thanks for joining us. As always, feel free to say hi in the chat, whether you're new or returning. But if you are new, I always like hearing where folks are from, so let us know where you're coming to us from. Richard, great to have you here. Yeah, we're doing our Vibe Coding Studio class later this month for our fellow math members, so it'd be great to start that here in a little under 3 weeks. So if you've joined Philomath, I'll be putting out some more information around kind of what's the structure of the class going to be. But that's not the subject of today's stream. We're going to do some Rosalind problems. We'll be looking specifically at alignment questions. So we're going to do global alignment, local alignment. These are classic algorithms in sequence analysis within computational biology. So we'll have a chance to implement them, which is always fun. We even implement these, I kind of teach this material at every imaginable level. We even implement these with our high school students when we teach our pre-college program at Carnegie Mellon every summer. So that's always a lot of fun. We don't tell students that it's hard. That's one of the keys. So if you want people to achieve something, you just don't tell them that it's hard and then set it up as a contest. And so our students do it as a hackathon challenge. And it turns out that they're all really good at doing it. So we have that program coming up in a few weeks too. So it's one of my favorite times of year as an educator. But how this is going to work today is I go through these problems kind of one at a time. And if you have any questions, let us know in the chat. Any comments, all that stuff. Be great to see it. I tend to address questions at the end. So after we've had a chance to go through an entire problem, if anybody has any questions, I always take those and kind of, cover those at the end. But we do one question at a time. We solve them all kind of independently. And today we're going to solve 6 questions all around global alignment. I think we're about ready to get started then. So we're going to look at this global alignment with scoring matrix problem first. And as you see, we have our starter code that I've copied over into our Rosalind folder. And I've updated custom IO and the data types files. So if you're following along, you can find those files in our starter code directory. We also have a completed code directory, and both of those are in the description of this video. But we're going to look at GLOB first. So we'll get here started with that momentarily. As always, please like and subscribe. It keeps us visible. You could even send us some sunshine or drop a comment in the chat or in the comment section of the video. And I think we're ready to get started. So let's code. GLOB is global alignment with scoring matrix. Now we've introduced a little bit about alignment previously when we've worked with some of these Rosalind challenges. Specifically, we looked at something called edit distance. And with edit distance is the minimum number of basically single character changes that are required to change one string into another string. So if we're working with something like genes, it's a very natural type of question to consider to say what's the simplest, most parsimonious explanation for how one of these genes might transform into another one of these genes. So in that particular case, we have an operation, which is changing a symbol, substituting it, inserting it, or deleting it. What's the fewest number of operations that I need to transform one string into another? We're going to generalize this because what we saw is with solving that question, we reduced it to a longest path in a directed network question. And in so doing, or I think maybe in that case it was a shortest path, but the idea was we're trying to obtain a recurrence relation, which is a formula for something in terms of, we have an expression for a function, which is equal to other terms of that function, usually with simpler inputs. So our classic example is the nth Fibonacci number, fib of n, is equal to fib of n minus 1 plus fib of n minus 2. So that's a recurrence relation saying that this number is equal to the sum of the two previous terms. In sequence alignment, we do this same sort of thing, but we try to frame everything as a longest path problem. And so what this problem is really getting at is that we're going to have a scoring table that will allow us to penalize each edit operation possibly differently. So by an edit operation, I mean a substitution of a symbol, insertion of a symbol, or deletion of a symbol. There are different scoring tables for this. I'll show you one. So one of these scoring tables is from the PAM family of scoring matrices. And you can see that in this particular case, these are amino acid symbols because we have 20 characters. So this is the standard collection of amino acids. And every number in that table tells us how much to reward or penalize aligning these two symbols in a growing alignment. So for example, if we were going to penalize an A against an M, and we saw that in an alignment, so we'd say an A got replaced with an M or vice versa, it would get a score of -1. So that's a penalty. A against an F gets a larger negative score of -3. A against W is really bad, so that gets a -6. But you'll notice sometimes even though you have a mismatch, you get a positive reward. So A against P or A against S or A against T all receive a +1. Along the main diagonal, you can see the match rewards for scoring C against a C is 12 or D against a D is 4. And over on the ends, you see that we have these -8s. So these are all corresponding to insertion or deletions. In this particular matrix, we've set all of those insertion or deletion of characters equal to a penalty of 8. So at the end of the day, what we're trying to find is an alignment of the two strings that allows us to insert gap symbols at certain points within these strings, but we can't move around the order of the symbols. And at the end of the day, we want to maximize the total score going column by column over that entire alignment with respect to the scoring matrix. So if we change the scoring matrix, we might change the alignment that we get at the end of the day. It's probably worth saying too, where is it that scoring tables like this come from? How is it that they get formed in the first place? And there are kind of two answers that I always try to point students towards as to why these tables exist. First and foremost, if we're working with protein alignments, well, the amino acids themselves have certain chemical properties. Amino acids are similar in general, but they all have a side chain, and those side chains can vary. Whatever the chemical structure is of the side chain produces an amino acid that might have different chemical properties. So you wind up with amino acids that are polar or that are positively or negatively charged. And so as a result, if we change one amino acid into one with very different chemical properties, that probably is going to cause a large change in the overarching structure of the protein. So for example, if I took an amino acid on the outside of a protein that's living in an aqueous solution, and I replaced it with a hydrophobic amino acid, that would not be a very chemically stable change because that amino acid is going to be trying to hide itself away from the water molecules that it's encountering. So chemical properties are an important reason for why this is the case. When you see these big negative numbers, a lot of the reason is with these mismatches, you're changing one amino acid for one with very different chemical properties. So it's not impossible to have that mutation, but it should receive a greater penalty because it's more rare. That's the second way that we can come at this problem, is to look at example alignments, possibly with simpler parameters, and then assessing how common each particular mutation is. So we can also say, well, this A against a W receives a penalty of -6 because we're not saying it's never possible for that to happen, but what we are saying is when we've constructed a collection of simple alignments from known data using more straightforward parameters, we just don't see A against a W as frequently as we would to see an A against a P, for example. So our new alignment algorithm should account for this. And when we've worked with edit distance, we don't take any of this into account. Our new problem formulation, therefore, is to say, well, we're going to take two protein strings as input, and the output that we want to produce is the best score of any alignment of the two strings. Notice we could also produce the alignment itself. That will require a little bit of backtracking, so we're not going to do that in this particular problem, but we could add to it. And what we want to produce at the end is this maximum alignment score, where we could also take the gap penalty as an input. So in that PAM matrix, the gap penalty was 8. We're just going to fix the gap penalty here for this particular problem to 5, but it's also going to be something that we can take, into account as a parameter, and probably should. We're also going to use the Blossom 62 scoring matrix, so that's a very commonly used matrix, and you'll see, well, there might be some slight disagreements between this and what we saw with the PAM matrix, but we see that A against a W still is getting a pretty big negative score. There still are positive mismatch values with A against, for example, an S. And so the relative values here are more or less in the same ballpark. Similarly, we saw an A against an A doesn't get a very big reward, but a C against a C does, and so forth. So we're going to use that scoring matrix. And we want to align these two strings, and at the end of the day, the best alignment of these two strings winds up with a score of 8. And that might make sense. We can see an E against an E and an E against an A there, E against an E, A against an A, and we also get our N here, and an N here, and an LY. So we're going to be able to pick up 5 matches from this alignment. We're also going to be having some penalties in certain places. And this string is, of course, longer than this string, so we're going to need to insert some gap symbols. But at the end of the day, our best scoring alignment here is going to have a score of 8. The idea is, regardless of what two input protein strings I'm given, I can always find what the best way of scoring the alignment between these two strings are. And what this number ultimately tells me is, biologically, how similar are these two strings? Our idea for solving this, then, is still going to be based off of the same algorithmic foundation as what we saw when we looked at edit distance, which means that we're going to be solving a longest path in a DAG problem, and we're going to be doing some dynamic programming, which means we're going to need a recurrence relation too. So I've got a figure. So I have a figure here that illustrates in a simpler level. How is it that we take what we learned about previously, which is forming a network from the two strings. So if our two strings were TG, TTA, and TC, GT, we would form these in this way, where the edges are sort of assigned to each symbol. And a path in this network corresponds to an alignment of the two strings. So if we go diagonally, where we would be aligning a T against a T, if we go vertically here, we would be taking the G and we would align it against a gap. If we move this way, we would be taking a gap in this string and aligning it against the C, and so forth. When we looked at edit distance, the idea was, well, every time you pick up a match, that's a good thing. So you would get a 0. Although if you use an edge like this is a mismatch because it's a T against a C. So in that particular case, you would have a score of -1. And what we're doing here is generalizing this. So one of the things that we could do to generalize it would be to take an arbitrary mismatch penalty that could vary, maybe set our match reward to 1, and then take this minus sigma as our penalty for a gap. So whenever we move horizontally or vertically, we would assess that the same fixed penalty. And what we saw with the PAM 250 matrix is that's always 8. What we're seeing for this particular problem is we want all these vertical or horizontal edges to be equal to -5. So every time we have to go vertically or horizontally, we're incorporating a mutation, that's an insertion or a deletion of a symbol, and we're going to penalize it with -5. And what we want to do is travel from the top left to the bottom right using sort of maximizing the total amount of score that we encounter along the way. What we're also going to do is for all of the diagonal edges, we'll just pull these from whatever the scoring table gives us. So this is a DNA alignment, so we won't have that, but if we have an amino acid alignment and we want to say, well, what is this edge? We would consider this symbol against this symbol, look it up in the table, and then weight that diagonal edge with whatever the table value gives us. So at the end of the day, we're still ultimately just trying to move from this node to this node and form an alignment that picks up as much total edge weights, the longest possible path that we can. Because it's a longest path problem, fortunately that means that we can use dynamic programming. The way in which we need to use dynamic programming is, well, we need a recurrence relation if we're going to achieve dynamic programming. So what we want to do is first establish that each of these nodes has a score associated with it. So you'd say there is some score at this node that indicates that the score here is the score of a best alignment up to this point in time. And what does that mean? Well, it's the best alignment of this substring, TGT, with whatever this substring is, TC. In that way, what we're looking for is the score at this node. But in the meantime, we can compute the scores at all these other nodes. And the reason why we do that is because these scores are easier to compute. This score is what we care about, but this score is actually really easy. In this case, it would just be minus sigma. In this case, it would be minus 2 sigma. And we can proceed in this way. So we could go across the row, and then the idea is once we've set sort of the first column and the first row, we can then look at a node like this. And this node is special after that point because, well, we know what this value is. We know what this value is. And so I'm really just consulting, the 3 predecessors of this particular node to say, well, what's the best way that I could enter this node? So if my alignment ended here, there's only 3 possibilities. I could come from above me to the left and diagonally. That idea, and I'm sort of keeping this simpler formulation of the question where all of the vertical and horizontal edges are all just getting a constant score, which is what the problem is going to do for us. So I'm just calling that sigma. In this problem, it's kind of hard-coded to 5, but in general, it could change. But once we have that, the idea is to say, well, what is the score at this node? You could have come from above me to the left or diagonally. And the best alignment here is going to be, well, the best alignment entering either of those 3 nodes. But then we have to take the edge weights into account too. So because I've traveled into that node, if I come horizontally or vertically, I need to subtract my sigma. If I come diagonally, then I need to look at whatever the score of that node is and then assess it, either a penalty or a reward, depending on, well, we would need to look at the corresponding symbols of the strings. So over here on the left, there is some symbol from string S, and over here on the top, there's some symbol of string T, and then I look up what's the score for those 2 values in my table, and that's what this edge weight becomes. So in the simpler case where we assign a negative mu penalty to any mismatch or a +1 reward, we would have these 2 cases. In the case of a scoring table, like Pam or Blossom, well, these values could take a wide array of different values depending on, well, it might be a reward, but it might be a larger reward or a smaller reward. And then this could be a mismatch, but it might actually be slightly positive or it might be very negative depending on the 2 symbols that we're actually aligning. So this final term winds up generalizing just a little bit to say, well, what is the match or mismatch reward or penalty associated with these 2 symbols? Now that we have this idea, the only thing that remains is to take it and just build a table of values where we start with the initial row and column, and then we proceed maybe row by row in the table, setting length of ij according to this recurrence relation that we see at every subsequent node that we encounter. That idea is going to bring us to an implementation. So our solution first, we should point out that in data types, we have a new user-defined class called a scoring matrix. And the scoring matrix really, just consists of two things. It consists of an alphabet, which is a list of strings. So this is the symbols that we care about. And then it also contains a collection of scores. So if we think about, well, what are the scores? For every pair of symbols from the alphabet, there's some score which I'm going to represent as a float, just to make it as general as possible. There's some score associated with that pair. So that sure sounds like key value pairs to me. And so a great way of representing this is to say it's a dictionary where the keys are tuples, so pairs of symbols, and the values are floats, which are the scores that we assign to those, which could be positive, negative, or zero. We also have one method, which is just for a particular scoring table, you can identify, you can pass in two strings or two symbols, and it will go in and access the scoring value associated with that pair. So nice simple class will be very useful here. What we want to do is to go to glob.py and implement this particular function. Now, there are two functions here. I've split this out to say what we really want to do is to form the entire scoring table. So to range through row by row and set all of the values according to the recurrence relation. Once I have that, though, I'm really only interested in the bottom right value. That's what's going to solve the question as asked. So we want to give, for this particular example, we want to give this value of 8. And if that's the case, well, I'm going to create the entire table first. So it's going to take S and T. It's going to take my scoring matrix as input. So this allows me to generalize it. It's not just Blossom 62. And it's going to take a gap penalty as indicated. So in this particular case, we're going to assume it's 5. But my solution is going to generalize this for any scoring matrix and any gap penalty. Custom IO also has Blossom 62. So this is the benefit of having a little bit of helper code so that you don't have to type. I think it's in here somewhere. Yeah. So that you never have to type manually out whatever these tables are. We went ahead and handled this for you so that if, whenever you have Blossom 62 or PAM 250 on the platform or whatever, you can just import it from Custom IO. So for that reason, regardless of what my matrix is and regardless of what my gap penalty is, I'm going to make this big table. And then at the end of the day, I want to return one value from that table. And it's the bottom right value. So I can get that with length of S and length of T as the row and column index in my table. You might say, well, wouldn't that be length of S minus 1 and length of T minus 1? And that would be a good question. So I will bring back just our alignment network. And if we look at our alignment network again, you'll notice this string has 5 symbols in it, but how many rows are there? There are 1, 2, 3, 4, 5, 6. So the rows are going to be indexed in a zero-based indexing system between 0 and the length of the string. Similarly, we have a string of length 4 along the columns, but we have 0, 1, 2, 3, 4 as the indices of those columns. So in general, the indices will range between 0 and length of S for the rows and 0 and length of T for the columns. This is a classic fence post problem because you have n plus 1 fence posts covering a distance of length n. So we need to be a little careful with our counting. And that's why I'm going to say the bottom right value is length of S as the row index and length of T as the column index. Once we have that, though, we need to actually apply our recurrence relation and build out the entire table. So the first thing that I will do is, well, let's build off of what I've just said in terms of knowing how big the table needs to be. So if we identify the size of the table, and what I'm given is S and T, well, we know then that the number of rows in the table is equal to the length of S plus 1. And the total number of columns is going to be the length of T plus 1, and they're going to be indexed 0 to length of T. And then the next thing I'll do is, set a bunch of 0 default values for the list. We can always update our scoring table later. But let's say I'm going to call that DP. It's a list of floats. And it's empty. And then I'll range over the number of rows. And I'll set the current row equal to a list of floats, which is a bunch of 0.0s times the number of calls. And then I will append it to DP. And there's a lot of ways of defining a num rows by num calls matrix of zeros, in Python at least. But that's one that I like because it's very steady and kind of generalizable. At the end of the process, of course, what I want to return is DP. And in the meantime, I need to be pretty careful, a little bit careful. So the first row and column come from accumulating gap penalties. So they're actually pretty easy to set. If we look one more time at our edge weights, in this particular case, where sigma is our gap penalty, the score at this node would be minus sigma, it would be minus 2 sigma here, it would be minus 3 sigma here. And in general, well, this is minus 1 times sigma, minus 2 times sigma, minus 3 times sigma. Notice this is column index 1, 2, 3. So the pattern's really easy. In general, in column K, the score at this node is minus K times sigma. And the same thing as we go down the columns. So as a result, what I would like to do then is to say, let's range over the number of rows. And if we're ranging over the number of rows, well, we're going to be in the initial column. So I'm going to set dp of I 0, just to indicate that we're in that initial column, equal to the negative of the gap penalty. We always assume that the gap penalty is positive. So that way we can express it as a penalty. We're getting a charge of $5 here, but then that means that we need to subtract it when we assign it to a penalty in the table, since it's something that needs to be negative. But in the ith row, well, we know that it's this gap penalty times I. And then we're going to range over the number of calls too. And here's where we're going to be setting everything in the initial row. So I'm going to be setting dp of 0 something. It's dp of 0 j. It's again going to be the negative gap penalty times our index, which is j. Finally, we want to range over the interior and apply the recurrence. And so we'll say for row and range over. We want to be careful. It'd be very easy to say num rows. But remember, we've already set the initial row and column. So we don't need to ever start our indexing at 0. We're going to start it at 1. And then we're going to have for call in range 1 over num calls. And now we have 3 possibilities, each receiving a variable. we're going to say we have up equals something, we have left equals something, and we have diagonal equals something. Here's where we think about, looking at our recurrence relation, where we said there's three possibilities. It could be the score above me plus the weight of the edge. It could be the score to the left of me plus the weight of the edge. Or it could be the score diagonally plus whatever the weight of the edge is. The first two cases are actually pretty straightforward. I can go one element up in a table by looking one row up. So dp of row minus 1, call. And it's going to be plus something. Now, in this particular case, I know what the edge weight is. It's just the gap penalty. And similarly, if I'm looking left, I'm still going to subtract the gap penalty, but I'm going one column previous. And so we set left equal to that. Finally, if I'm going diagonally, well, I know in that particular case that I need to be consulting row minus 1, col minus 1 as my indices. But it's not quite as clear cut, that I'm always going to have a constant value on this edge. Here's where I need to say, well, what is the score of the two symbols that I'm interested in? So the two symbols that I'm interested in are S of row minus 1, because the row index is kind of indexing the symbols of S. And in terms of T, I need to be looking at col minus 1. So those are the two symbols that I care about. And then the question becomes, are they similar to each other? Are they very different? They might be identical, but even if they're not identical, this could be a positive score. This is where what we want to do is simply look up in the table. So here's where we call our score method from the scoring matrix that takes my two symbols that I care about and returns their score. Whatever the score is between those, that's what the edge weight in this network behind the scenes is going to be. Once I've got those three possibilities, the current value is just the max of the three. So we can say dp of row col is equal to the maximum of the up, the left, and the diagonal values. And that's really it. This is doing something that in 1970 was new research, and that these days is something we can code with really, a few dozen lines of code, as long as we understand the algorithmic paradigm, which is where the power comes from. And that's dynamic programming, and taking this string problem and reframing it as something that we can conceptualize, at least, as finding the longest path in a network. That's all very powerful. And when we move towards that paradigm, it means that we can frame any kind of sequence alignment question that we like, often in this same kind of frame as it's a longest path in some network. And when we do that, that means if it's a longest path in a directed acyclic network, that's a solved problem. We know that the score at a node is always equal to the maximum of all of its predecessors plus the edge weights. So we're going to just apply that concept over and over and over again in the context of sequence alignment to solve different variants of sequence alignments. Now, I'm making a claim that we've actually solved this question. So probably what we should do is to go to the platform and download a data set. Or really, I could, first and foremost, I could check and make sure everything's working here. So I could Python 3 glob.py. We get an answer of 8. That's good. So the code appears to be running. And in the meantime, I downloaded a data set. Need to put it somewhere. So let me bring back my File Explorer. And I'm going to rename it data set. And then in glob.py, you can see here are our two very realistic amino acid strings. We want to align them and find the best score of any possible alignment of them. I'm going to, in main, uncomment out the parsing part of the code. So when I run this again, I get an answer of 2066 that gets printed, as well as written to a file, but it's just 2066. So I could even type that in. And that's the answer. Now, this leaves a little to be desired. What's interesting about this is we've solved a problem behind the scenes that is pretty powerful, right? We found over all the different ways of sliding these two large strings along each other and adding gap symbols and trying to maximize, the score between them to make them line up as similarly as possible using this scoring matrix. Even though we've done that, what we would like to also have is the alignment itself. So in order to do that, we need to do what we did in the edit alignment question. EDTA is its ID. And we would also need to backtrack. So once we have the scoring table, we then need to ask the question of, well, which direction did you come from? And we can start at the end and say, which direction did you come from to get this optimal value? And whether it's left, up, or diagonal, continue tracing back at every node, asking where you came from, and that forms our longest path that we care about. That having been said, we're going to do that here in a minute for another problem, but for this problem, we've solved the problem and we're going to move on. If you have any questions, let me know. Sarah, welcome. Thanks for joining us. We'll look at counting optimal alignments next, CTEA. So get rid of my data set and clean everything up. All right. CTEA is counting optimal alignments. And there's a natural setup for what this question is trying to do. This question is asking really a counting question, which is what a lot of the questions on Rosalind get at. But I think the idea is to count something, but to understand why it is that we're counting it. And to zoom out just a little bit from this, there's a common phenomenon that's arising, I think that arises in a variety of different types of contexts. And it's very important in biology. So I'm going to make a deep point first, which is a lot of times you might try and frame a question as like an optimization problem. I want to find the best thing from this set that explains this data. So, and it could be the most parsimonious explanation. So by best, maybe it's like the minimum score and so forth. But then, well, there's 2 points. One is you could have multiple things achieving that best score. Or you could have multiple things that are very close to the best score. And then a question becomes, well, you really could have multiple candidate solutions. And how similar are those candidate solutions? So it would be fine, for example, imagine you have evolutionary tree construction software. And it's able to assign for, you give it 2,000 species, the same gene for 2,000 species or whatever. And it produces, a mechanism for saying, here's a tree and here's a score of how good we feel about, this tree's explanation of the data. But then you could also look at, well, what would happen if you look at your top 100 trees? And the natural question you would have is, are the top 100 trees similar to each other? Because your algorithm probably isn't any good if you produce 100 different explanations of this data that are all wildly different. So this is called stability of solutions to some kind of problem that you care about. It's a simple but deep idea. And you might ask the same thing about our alignment algorithms, which are, okay, I can align two strings. But at the end of the day, there might be different ways of aligning two strings. And the scores that you would get as a result of that might be similar, but you wind up with different alignments entirely. Well, that would be a bad thing, right? Because when we align two strings, the idea is that this is the biological explanation for this. Here's how these strings differ, and here are the reasons why. So if you were producing a lot of different solutions and they were all very different from each other, it would be very hard to make any biological conclusions. It turns out that in the grand scheme of things, this is not a major concern to worry about. However, sometimes you can have, especially for some parameters, you can have a lot of different possible solutions that might wind up being similar, but that all actually achieve the same optimal solution in terms of the final score that you get. So in particular, where does this come from? Well, if I'm in the scoring table somewhere, and I could have come from above me, to the left of me, or diagonally, and I have those three options, well, what if there's a tie? And so if there's a tie, maybe I could have come from above me or to the left if those two values tie. And so those ties are going to propagate, and they're going to cause, multiple solutions to exist as you move through the grid. Sometimes you only have one option, and so you just say, well, essentially, if I only could have come from above, that is the only thing that achieves the maximum. Well, how many alignments are there that are correct, like optimal alignments ending at my particular node? It's going to be the number that come from above me. But if there's two different directions, it's going to be the number that come from each of those directions, and we're going to sum them. So that leads us to the problem, which is that we have two protein strings or whatever strings. And what's the number of optimal alignments of these with respect to some scoring function? And with respect to what's nice about the scoring matrices is that data set is very rich, right? So every pair of symbols receives a different score. As a result, you're not actually going to get that many ties, and you're not going to generate huge numbers of optimal alignments. This is one of the reasons why the scoring table is such a good construct, because it gives you, the ability to actually truly pick one or a very small number of alignments and have a lot of confidence that with respect to that scoring table, this is the correct alignment. Edit distance, though, doesn't necessarily lead you that way, because remember, the edit distance doesn't differentiate between what this particular pair of symbols is. It just says if it's a mismatch, it's going to essentially receive a penalty of 1. And if it's an insertion or deletion, same thing. At the end of the day, we're just going to be adding up all of the number of operations that are required to change one string into another. But the idea is, well, we could have changed them in very different ways. So it turns out that if you generate two strings with 1,000 amino acids, and then you ask, what are the different ways that you could have changed one string into another, where you're not thinking about the particular penalties associated with each swap of symbols, all of a sudden the number of alignments are going to explode. So the hint here is we're doing this with the remainder of 2 to the 27 minus 1. And you say, why would we do that? Well, a lot of times when you start adding or multiplying things and you want to take the remainder by something, if we just did 1,000,000, imagine what would happen. So this says, imagine what would happen if we're doing a modulo 10. If at any point in time you multiply by a multiple of 10, then everybody from that point forward, if we're doing a lot of multiplications, everybody winds up being divisible by 10. And so the answer would just be 0. So to prevent that sort of issue, we'd take the remainder by a prime. The only way that you could ever, be divisible by a prime is if, or have this circumstance happen, is if you're divisible by the prime itself, instead of like maybe a bunch of different multiplications by 10 that would get you to be divisible by 1,000,000 very quickly. But with prime numbers, that can't happen. So it's a very minor point, and it's why there's this very weird modulus here. It's just a big prime number that we're going to be taking the remainder by. Again, we take the remainder y because a lot of these numbers grow so big that it would become unmanageable or unwieldy in at least some programming languages to even try and provide the answer to the question. So the purpose of this question is subtly that with edit distance, you can't really trust the answers that you get because there are going to be so many of them. Whereas with something like global alignment, the situation is quite a bit different because you get that richer data set of a scoring matrix. Let's solve this question though. And our solution is we're going to build the edit scoring table, a problem that we've already solved in EDIT. But as we build the scoring table, we're also going to keep track of the number of alignments up to the current point in the table, meaning it's an alignment of two prefixes of S and T that are optimal. And in order to do that, we'll say, well, coming from each of the possible directions, if there is a tie, I'm going to sum from each of those tied directions the number of solutions up to the point in time that I've hit there. So we've got a function called count optimal alignments. The first thing it needs to do is to import the edit table from the edit problem that we solved. And once I've imported it, I want to set my table to be equal to it. So it's just going to take S and T. I can know what the number of rows and calls is going to be. I know that they're length of S plus 1 and length of T plus 1. I could get that from S or T. I could get it from the table. And now we're going to initialize a new table to store the number of alignments achieving the max with respect to edit distance. I guess it's a min, so I'll say optimum. And it's of S up to position I, so the prefix of S up to this point, and the prefix of T up to this point as well. So if we want to, initialize that table, we know how big it needs to be. I'm going to call it count, and it's a list of two-dimensional list of integers. It's going to start off as empty. And I want to say for I and range over the number of rows. I'll say, probably give it some parentheses here so Python doesn't get mad. I'll say row is a list of integers that's empty, and I'll append it as we go. Now at the end, we want to return the count, but that would return an entire table. Returning an entire table is not exactly what we want to do. We want to just return the number of optimal alignments of the entire string. And remember, the value of this table at position ij is going to store the number of alignments achieving the optimum of the prefix of S going up to position I and the prefix of T going up to position J. So at the end of the day, we want the bottom right element. And I can do that by saying return count of length of S as the row index and length of T as the column index, which we know. So number of rows is length of S plus 1, number of calls is length of T plus 1. So that gives us that for the final row index and length of T for the final column index. So we've initialized the matrix. At the end of the day, we're going to return the bottom right element. We might then also say, well, let's do the first row and column. And the path to any node in this row call is unique. So count should be 1. So I'll say for I and range over the num rows. If we're ranging over the number of rows, well, that's going to be the row index. The column index is 0, and we're just setting that count value to 1. We're going to range also over the number of calls. And I'm going to set count of 0j equal to 1. And then we're going to apply the same kind of idea that we saw with global alignment, which is we're going to range over the interior and set all of its values. Okay, and the idea is whenever we see a tie, we will add the contribution from all nodes achieving the tie. So here's where having the edit distance table which we called dp, is going to be particularly useful because I can say at this position, where did I come from in that table? I could have come from more than one place, but anywhere that I came from is going to contribute to my current value of count ij. And so here I'll say we're ranging over the interior, so I know I'm ranging my row index starting at 1 and going up to and not including num rows. The column index is similar. And then I want to consult my 3 values. So I'm going to say we have an up value, and the up value is, I'm looking at the edit table. So this is 1 row up. And if I'm looking up, I've added an edit value. So the edge weight would be 1. If I'm looking left, we look at dp of row col -1, and it's a horizontal edge, so it means it's a insertion or deletion, so it's a +1 as well. I'm adding an operation. And then we've got a match versus a mismatch. So we have 2 cases here, but we're going to say if it's the case that the current symbol of S, which is S of row -1, is equal to the current symbol of T, which is T of col -1. Well, this is our match case, so the diag value is equal to dp of row -1, col -1, and the reason why is that, this is a +0, so there's no penalty associated with that particular operation. The else is that, well, it's a mismatch, so penalty. So we'll take diag equal to the value above and to the left, but then we're going to add 1 to it. Then at this point in time, we say which predecessor, and it could be more than one, achieves, this dp of row col value that we are taking for granted because it was already set. So I'm going to say that the best value is equal to dp of row col. And I'll say the number of solutions at this particular node is going to be equal to 0. I'm going to set it here. But now we go through the 3 cases. So we're going to range through the 3 cases and say, is it the case that up is equal to the best? So if best is equal to this up value, then we know that we could have come from above. So there are optimal solutions that come from the node above me in this table or in this network. And if that's the case, well, I'll say num solutions plus equal count of one above me as a row index that's 1 smaller, and I'm in the same column. Now, the issue becomes we also need to take into account the modulus, which is just kind of annoying. And that modulus could be also an input here, but we have it as this global constant. Whichever way we want to do it, this is the correct solution to the question if we're just counting all the solutions, but we're going to need to add the modulus. I'm going to do it here in a second. In the meantime, I'm going to say, well, if left is equal to best, I'm going to do the same thing. Number of solutions is going to be its current value plus what happens when we're in the same row, but we're 1 column previous. You'll note this is not an else if, because both of these things could be true. It may be the case that I could come into this node with optimal solutions that come from the left or above me. And regardless of which of those cases is true, one of them might be true, 0 of them might be true, or both might be true. But if they're both true, I want to contribute their solutions to num solutions. So finally, I have if diag equal best. All of these 3 things I guessed could be true, and num solutions is going to get plus equaled count of row -1, col -1, because that's looking at our diagonal value. Then after all of this, I've identified however many solutions I have. Count row of col is just equal to the number of solutions. So this is, I can finally set my value of the count table. And that is our answer, right? But I need to take into account the modulus. So here's where the annoying part happens, which is that I do have to say equal num solutions plus this. And then after I figure out this value, I then have to percent it and take the remainder by our mod. And then I need to apply the same idea all the way down. So I'll do it there. I'll do it here too. And it's not too bad. We should, of course, make sure that our code is reasonable and that it appears to be working on our sample data. So we're going to say Python 3 CTEA.py. And of course, I've got an issue. I've got a list assignment index out of range. All right, line 37, line 78. 37 is here. Doesn't seem too bad. Counted by 0 is equal to 1. This doesn't seem ideal. That would definitely explain why there's no values there. So let's make sure that the row has data there. Okay, well, we have a different issue here. Line 64, line 78, 54. Arranging everything appropriately here, that's good. It doesn't like just going to print this array. Oh. I don't have a count here. Let's see, I could at least take a look at count. Let's try this one more time. Okay, we got 4. Whew. All right. So now I can download a data set. All right, we're back on the tracks. And dataset.txt. Again, we have a very realistic looking data set here, which is good. I can get rid of this multi-line comment here. So now we're running it on the real data set. And as I promised, we're going to get a huge number. The actual number is much bigger than that, but this is when we take the remainder by that prime number, which is this number. All right, and we get a correct solution. So as I said, if you look at a real global alignment circumstance, this is why we don't want to settle for edit alignment, because you're going to get a huge, like exponentially growing number of possible solutions that are all optimal. Some of them might be more similar to each other than others, but we need much more than just, oh, it's an insertion or a deletion, it's a penalty of 1, and if it's a mismatch, it's just an arbitrary penalty. That's where that's going to lead us to having all these solutions. and where global alignment will shine because you won't have as many. If you don't believe me, I'd say, go and grab your favorite 2 genes that are similar to each other and take what we did with global alignment and instead of, implementing it by taking the edit table, do the same thing for importing from GLOB, because now we have a global alignment table. You're going to need to specify a certain matrix here. But let me know what you get, right? Like, try this whole process again. I'm in the wrong problem. Try this whole process again, maybe without even performing the modulus, but count optimal alignments where instead of calling DP as edit table, I don't know, give it the global alignment scoring table as well. And I'll leave that as a little bit of homework for you. So it won't require that much change, but pick your favorite matrix, Blossom 62, PM250, doesn't matter. Do this exact same process again and let me know how many solutions you get that achieve the optimum. It'd be cool actually to see it without the modulus in the case of the edit distance and global. I mean, we could do this live, but we've got 6 problems to cover, and I'd rather you just let me know what you find. Any questions, let me know. Otherwise, we're going to go on to GCON. Okay. GCON is global alignment with constant gap penalty. And we've been working with, whether it's edit distance or global alignment, we have a model of insertions or deletions that assumes that each symbol contributes some penalty. In the case of edit distance, that penalty is 1. When we worked with global alignment before, we generalized this to a parameter that the platform likes just using a standard value of 5 hard-coded, although it really could take that parameter as input. That's probably a better formulation of the problem. And in practice, the question becomes, is that too harsh? So you might imagine there's one mutation that's responsible for deleting or inserting a bunch of consecutive symbols in a gene. So imagine that it's 18 symbols. The point becomes, do we really want to charge this operation 18 times whatever the gap penalty is? That seems like a harsh penalty. And that's a good idea, right? Which is, we need to take into account the length of the inserted or deleted region so that we're not overcharging one operation that just happens to have a lot of inserted or deleted symbols in it. Now, you might say, if I delete 18 symbols from a DNA string, there's a good chance that's going to be pretty deleterious to the organism if we're inside of a protein. And I would agree with that, but that doesn't mean that we need to charge it as 18 times 5. So what this problem is going to do is it's going to do something that I think the biologists would be pretty angry at us for doing. And we're going to do a better version of it later. But this is a warm-up question to think about, well, what if it were the case that we didn't charge each symbol with its own penalty? What if we said anytime you see a contiguous region, when you align these 2 strings, anytime you see a contiguous run of gap symbols, that's just going to get a constant penalty. And so that's what we say of a constant gap penalty equal to 5. It is not a biologically good thing to do to go this extreme, to say every single deletion, whether it's short or large, is going to get a constant penalty. What we want is this Goldilocks penalty, which says, yeah, longer runs of gaps should get a bigger score, But saying it that 18 symbols means 18 times 5 is the penalty, that's very harsh. And so can we find something in between the two? The in-between Goldilocks value is going to be called affine alignment. I'm going to probably kind of very briefly reference it here, but it's a separate problem that we're going to look at in a later question. For now, I would point out, well, how is it that we would change our alignment network? How would we think about that alignment network changing if we moved towards constant gap penalties? And what I would say is, well, imagine in our first formulation of this as a network problem, we're moving from top left to bottom right in our alignment network. And we know that the diagonal edges are matches or mismatches. These vertical and horizontal ones are indels. And if we had previously, we had two consecutive vertical edges or two consecutive horizontal edges, we would charge them with a penalty of 2 times whatever the edge weight was. So as we're racking up a score, we might get a match reward, but then we're going to get, 2 different vertical edge penalties here, and then another match or mismatch, whatever, and then 2 different horizontal penalties and so forth. But in the constant penalty formulation of this, we're really thinking of allowing ourselves to jump over a node and have this longer gap, and that this gap would then be assigned whatever our constant penalty is, which in this particular problem, it has this hard-coded value of 5. But that means we would need to allow, this vertical edge and this vertical edge too, and basically any 2 nodes that are in the same row or the same column are going to get a horizontal or a vertical edge connecting them respectively. And at the end of the day, what this is going to cause is a network where we're still finding the longest path from top left to bottom right, where sometimes we can make these big jumps, but one where the number of edges is blowing up. And the number of edges blowing up is bad, because when we compute our occurrence relation, when I'm at a node, that node is the maximum over, well, all of the nodes that lead into me plus their edge weights. And so if I have a bunch of nodes that are connected to me, like this node will be connected from here and here and here and here, as well as from here and here and here and here, on average, if you have 2 strings of length n, the average case is like you're in the middle of the network. You have n over 2 edges coming from my left in the same row, and n over 2 edges coming from above me in the same column. And as a result, when I have my recurrence relation, I'm going to have to compute a lot of things. And that's going to essentially multiply the runtime of my algorithm by a factor of n. And that's going to be bad, because sequence alignment is, something that we want to scale well. Global alignment does scale well. It's taking runtime of, about n squared, because you have n squared values to set. And each one is only taking in a constant amount of information. But if you blow up that amount of information that each node has to use in the recurrence relation, that's going to multiply the runtime by a factor of n. That's really bad if we're aligning 2 genes of, say, length 10,000. So now I've expanded my runtime by a factor of length 10,000. We're going to really start to notice that. And if we want to run our algorithms, I don't know, in parallel on a bunch of different pairs of genes, that's going to be pretty suboptimal. So there's a different solution. I think when students see the different solution for the first time, it might not be the most obviously intuitive thing, but if you always think about, well, we're trying to remove edges from our network. Edges are bad because they mean that when I compute my recurrence relation, I'm going to have to use those edges to factor in possible scores. The more clever solution is to transition towards a 3-layer network. So instead of just having nodes in one layer, we actually are going to have one layer that's devoted to like indels in the vertical direction, and another layer on the right here that's devoted to indels in the horizontal direction. And I'm giving you a preview of how we're going to handle this when we move towards affine gap penalties. So with affine gap penalties, you're charged a value of sigma for starting the gap. So any gap has a value of sigma, but then each additional symbol receives a smaller penalty, which we refer to as epsilon. Now, in this particular case, we have an easier example of this. So when we solve the global affine alignment problem, we will come back to this particular figure. In this case, though, well, our constant gap penalty that we're charging is going to, so imagine that I'm at this particular node. This is the same picture that we had previously. So trying to get it all in one place for us to see. That might be tough. Yeah. Okay. So this was the path that we had previously. If we have long indel edges, well, it changes into this. This is actually the same path. So we start at the top left, our source node. We have a match node. But instead of jumping down, we move over to a different layer and then move down and then come back. And you'll notice that every node over here only really has two edges into it. So it has an edge that comes from the starting layer, and it has an edge that comes from above me, but it doesn't have any other edges. So even though we've added a bunch of nodes, each node only has either 2 or 3 predecessors. So you have 2 here. Over here you have one coming from my left, but also one coming from the middle layer. And in the middle layer, well, I have one coming diagonally and above me, but I'll have one that returns and jumps back from the corresponding place in the lower or upper layer corresponding to my indels. So at the end of the day, I'm still going from top left to bottom right. I'm still trying to do that with maximum score. All my matches here are, these edges are like matches or mismatches of the corresponding symbols. Those are all the same. But now anytime I leave this layer and move towards like this vertical deletion layer, I'm going to assign a charge of minus sigma. This edge, every subsequent edge that I add onto it is just not going to contribute. So all these edge weights are going to be 0. All these edge weights over here are going to be 0. We'll come back to this later when we talk about our epsilon, because that's going to be adding additional symbols here. So I'm giving you a preview of how we solve what's called affine alignment. But for now, all these edge weights are 0. So what's nice about that is we're still going to have a recurrence relation. In this upper or lower level, you can only come from the middle. And if you come from the middle, you're getting this value of minus sigma as your edge weight. So you see that's the same in either case. Or you could be staying in the layer, in which case it's really just the node to my left or above me, depending on whether you're in the lower or upper level. And so our recurrence relation is just lower of I minus 1j or upper of ij minus 1. So all these nodes actually are really easy to set their recurrence relations of. The middle layer is a little trickier. If I'm in the middle layer, like here, I could have come from this diagonal edge, or I could have closed out a gap and come back and returned to that node from the upper or the lower layers, but I don't actually charge that to like a penalty for that. So you have a bunch of plus zeros here. So this recurrence relation is going to be what we use in order to solve our problem. I'm just going to build 3 tables instead of 1. And each table is going to have its corresponding recurrence relations that I set. And then at the end of the day, I'm interested in what's in the bottom right value. So I will technically be interested in 3 values. I'll be interested in this value, and this value. And I'll say whichever of those is the biggest is going to be my winner. So the reason why that's the case is I actually could end the alignment in a gap, and that's okay. I don't have to rush back here. Or I could explicitly add, an edge weight back in this direction that I take account of. Either way, I'm basically just looking for the bottom right value that I care about and say which of those 3 is the biggest after I apply all these recurrence relations. That's magically, amazingly going to tell me the best score of any global alignment with these constant penalties. Okay. So I think we know enough now to do a little bit of code. And what I want to do is the same thing that we've seen before. I've got one function that's going to produce scoring tables, and you're going to notice, what's the output here? The output here is 3 different scoring tables. So it's a tuple of 3 different 2-dimensional lists of floats. I will write that function second. The first function is going to say, well, if I've got that function, it's going to give me the middle, the lower, and the upper scoring tables. So I'm going to say take ST, the scoring matrix, and the gap penalty. And once I've got it, I'll say, there are 3 values that I care about. It's the final middle value, which is middle of length of S, length of T. So that's the bottom right value in the middle layer. We could have the bottom right value in the upper layer. Or we could have the bottom right value in the lower layer. And whichever of those three is the biggest, we're going to return as the maximum. So we're going to say it's the maximum of final middle, final upper, and final lower. And that's going to be our function. So this defers all the work to this function called constant gap tables that will produce the middle, the upper, and the lower in that order, applying our recurrence relation. We also have this very large negative infinity value that's just kind of a placeholder value that's going to say, like, this particular position is not reachable within the tables. But largely, we're still going to initialize in the same way. So we're going to have number of rows is equal to the length of S plus 1. And number of calls is equal to the length of T plus 1. And those are going to be the dimensions of our table regardless of which table we're in. So let's initialize each of the three scoring tables. And we can use negative infinity here. I think that will be useful. So middle is a list of lists of floats. It's equal to empty. Same thing for upper. And same thing for lower. So we'll say for I in range over the num rows. And the middle row is a list of floats. It's equal to negative infinity times the number of calls. And I'll do the same thing for an upper row and a lower row. And once I've got that, I'll say middle dot append middle row, lower dot append lower row, and we'll keep them in the same order. All that just kind of creates our data. Now everybody has these same negative infinity values. And our first value that we care about is, the source node is where we start. So it should get a value of 0. So I know I can comfortably say that the middle of 0, 0 is just equal to 0. Then there's an initial column or row 2, which is, align the prefix of S up to position I against an empty string. So against all, gap symbols. And this is just one gap. Before we were accumulating penalties as we went. But this time, when I say range over all the rows that you care about, when we set the value that we care about, it's upper of I 0, and it's equal to the negative of the gap penalty. Okay. Before it would be times I, but remember it's a constant penalty, so we can jump anywhere in that first row we like just for the gap penalty. Notice too, we're setting all of these upper values. So we're jumping from this node to here, to here, to here, to here, to here. And you'll notice, well, I actually can't really, I can reach this value, but I'm not able to set this value yet because I need all these values. The only way I can actually reach this value is if I came back from this node to here, or I guess from this node to here, but I can't even come back from that node. So the only way I could return is here, and so I can't actually set this row or this column of the middle layer quite yet. So I have to be clever. I need to set, all of these values first, and then all of these values first. I've set the upper level, and what I'll do is set the lower level. So now I'll have a 4J in range, starting at 1, going up to the number of calls. And making sure I've got everything here. This will be lower of 0, J, is also equal to negative gap penalty. Okay. And I have very minor point. I think for consistency with my figure, I need to do it this way. Shouldn't change a whole lot. I might have to switch some things, but this makes sure that when I look at my figure, this is upper of 0J, and this is lower of I0. So, this is just making sure that the green and the blue tables could be easily switched. And as long as I agree on a formulation here. And so the formulation I'm going to have is going to be consistent with the figure. So when we're looking at the lower table and we're setting these values, these are all in column 0. All these values are in row 0. So you'll see upper is in row 0, lower is in column 0. And way down at the end, I want to return middle, upper, lower. But in the meantime, I've set the values that I care about in terms of the first row and column. I'm going to range over the interior and apply the recurrence. So that would be a good thing to do. And we know how to do that. We'll say for row in range over 1 to number of rows. For call in range of 1 to num calls. I'll say that the substitution score that I care about is, well, the weight of the diagonal edge. So this is matrix.score of S of row minus 1 and T of call minus 1. And then I've got a from middle, which is, if I look at the value above me and add the contribution of that subscore, it could have come from the middle. I also could have come from the upper. So this is, if I came from the upper layer, we look back at our figure, and I'm at a particular node, like this particular node. Notice it's at the same position that we had before. So I'm really just looking at upper of ij, and similarly, I'm going to look at lower of ij. The other thing, though, is if I'm coming back into this position, then I'm eventually going to be using this diagonal edge. So we're going to say upper of row minus 1, call minus 1, and then plus that subscore. And then we'll have from lower is equal to the lower value plus the subscore for that. And then the middle of row call is equal to the lower of, the max of these three things. So from middle, from upper, from lower. And that's a little bit different to the recurrence relation that we showed, but the idea here is we're going to be, if we're coming back to a particular place, we're returning to the middle layer. I think the idea is that we're going to be like taking the character substitution at this particular point in time when we close that gap. And it's just, we're taking those two things and combining them. So now we just need to handle the upper and the lower recurrence relations. And we're going to do that in this same loop. So I'll say, there's also a recurrence that says we could kind of open the upper layer by coming from the appropriate place in the middle. And if we're coming from the appropriate place in the middle, like we're starting a gap. And if we're starting a gap, then we look at our upper layer. Drag it. Look at our upper layer. And it's telling me, at this particular place in the upper side of things, I'm coming from one column previously, and I'm coming from the same row. So this is going to be middle of row, call -1. And I've started the gap penalty, so I'm going to charge it at this point in time. And I'll have kind of an open lower, and I'm looking at the middle, but I'm looking at row -1 call. So this is where I'm looking one value kind of above me in the middle. And I'm also going to subtract the gap penalty. And here's where we're looking kind of a little bit ahead towards affine gap penalties. So if I'm at this node, the other possibility is I could have come from the left. Or I'm at this node, I could have come from the left. And that receives, a charge of 0. So I also have an upper extend. I'll call it extend upper. And this is where I'll say it's still in the same row, but it's one column over, and it's +0. So there is no charge. And there's an extend lower, which is lower of row -1 and call, also +0. Okay. Now once I've got that, so I've got my open upper, my extend upper, and I've got each of these cases. Well, I want to set upper of row call equal to the max of those two things. So here's where I apply my recurrence. Do it that way. Or we're going to set lower of row call equal to the max of the two things that it could come from. So it could be open lower, or it could be extend lower. And now we have our three matrices that we're going to return. So hopefully this works. I switched lower and upper kind of midstream here just to make sure that it represents the same figure. So the odds of this working on our sample are probably low. Let's see. Oh, we get an expected value of 13. All right. So now we should be able to download a data set. And once we've got our randomized data set, we'll add it, call it dataset.txt. I already have one. Probably should clean that up. And we'll get rid of our comments around the parsing part of the code, run it again. And hopefully the answer is 2839. All right. So we get an answer there. I'm not tremendously in love with that problem because it's not biologically appropriate. Like, you're never going to find a constant gap penalty. And if you take anything from it, the number one thing is to take that, well, the idea was good of saying, well, if I have 100 consecutive symbols deleted, I probably shouldn't treat that as 100 separate operations. It should be one operation, but treating that as also the same as deleting one symbol is also biologically bad. So we will resolve this. We'll come back to it, and we'll see a problem that's very similar later when we look at affine gap penalties, but that's the subject for another day. All right. We had a question about when we looked at Fibonacci sequences, should we use the iterative way or recursive way to compute Fibonacci? Well, that's in maybe our first stream. So we have problems on that you can check out. I also, when we first covered dynamic programming, there's another stream where we looked at that. And we looked at the major pitfalls of computing Fibonacci sequences recursively, at least under the traditional way of performing recursion. So if you haven't tried to do that, you can follow that old stream or check out that problem. And you'll see that, you're going to encounter some major problems there. As we say, big tree bad. All right, so we're going to look at local alignment next. And I'll get us ready for that. We got 3 more problems today. Whereas GCON's not the most cutting edge applicable question, the next question very much is. Very much is. All right. Okay. LOCA is local alignment with scoring matrix. And what this problem is going to get at is that we've aligned strings globally, whether we're looking at edit distance or global alignment, and regardless of whether we're working with constant or linear penalties. In any particular case, the idea is I have 2 strings. I want to line them up and figure out where the differences are in a way that makes the most sense as possible. But a lot of times, we're not interested in aligning the entire genes. What we're interested in is finding local regions of similarity. And if we're interested in local regions of similarity, what do we mean by that? So what we're particularly interested in is, places within each string that when we align those particular places, that's where we see a good score. So you might imagine that you could produce an alignment where the 2 strings have a small region of extreme similarity, and that's what we want to find. But unfortunately, what will happen is if that's their only real region of similarity, and then we try to globally align them, that region of similarity might get kind of washed out, and we instead return, and going back to the point of stability that we made in a previous problem, that signal might kind of get washed out in the mix of the fact that there's so many mutations, you might not be able to guarantee that that particular path that's going to lead you through this region of extreme similarity is going to be found because we're incorporating a global alignment that winds up producing all of these penalties. So what we would like to do instead to set this up is to ignore everything outside of a particular region of the two strings. Now, we don't know what that region of similarity is in advance, which is what makes this a hard problem. But if we knew, for example, that there was some region of the strings where you get a really good score, then you'd be in good shape. So in this case, we're going to take two strings as input, and we're going to maximize the alignment score, but we're going to maximize the alignment score of, hang on. Maximize the alignment score of these two strings where we're looking at substrings of the two strings. And so we're still going to take a PAM 250 scoring matrix, for example, as input, and we're still going to take like a linear gap penalty. We're going back to linear gap penalties. But what we want is the best scoring alignment of like two substrings of what we see. So the question becomes how to solve that. And from the perspective of having a history lesson, the problem that we're looking at here, which is like the best scoring alignment of substrings of two strings, was unsolved for 10 years. Like the entire 1970s, this problem essentially had no fast known solution. And there's a great insight here, and the great insight comes from being able to formulate our question as a longest path in a network question. So if we imagine that we have two strings here, and there's a region of similarity that we see, if you zoom in far enough, you can see, well, you have like CAG-TTAT, and you have CAG-TCTAT, but you have a lot of similarity. The problem becomes reaching this point would accumulate a huge amount of like insertions or deletions, whichever way you see it. And reaching, like getting from here to the final node would also incorporate a lot of vertical edges, which is going to produce like a lot of penalties. And so the point becomes, how can we get around that? And the insight here of getting around it is to simply allow ourselves to start anywhere that we like for free, and allow ourselves to end anywhere in the alignment for free as well. And so if we think about, starting here for free, what that means is that essentially every node in our network is going to be reachable from the source, but reachable from the source with what we call a free taxi ride. So we have an entire chapter that gets into very deep details in bioinformatics algorithms. So you can check out our textbook if you're interested in a much deeper explanation of all this. But at the end of the day, the insight was that we have the same three elements of our recurrence relation that we had before, but literally all we are going to do is to add a single zero term that you see here to the recurrence, corresponding to being able to start at this particular node without incorporating any penalties for doing so. So it's a genius insight from Smith-Waterman. After 10 years of futile work in this area, which is hard to believe these days, because if you had, AI would solve this. If it didn't know this, it would solve this question immediately. So we had a 10 and a half year gap where humanity just didn't know how to solve this question. And the idea here is, well, every node gets this one additional term of the recurrence. And then at the end, you have to handle the process of the alignment could end anywhere. So what we will do is we're treating this as kind of like you have a free ride from anywhere to the sink. And if that's the case, then at the end of the process, really what we're going to do is make our table, and then whatever the maximum value across the entire table is, maybe it's here, that's where we're going to end our local alignment. So the local alignment will end at the maximum value in the table. And we're going to say, well, where does it start? It starts when, as we go backwards, the first point at which we hit a zero value, because then we can just jump back to the beginning. So if the scoring value here is 174, well, we know we're not going to be coming from here because that 174 did not get set as a value of 0. So it must be carrying on backwards as we go. So the solution then is going to be similar to what we've seen before. When we look at actually coding this, the solution is going to be essentially global alignment. I'm even going to do something a little bit dangerous, which is I want to make a local alignment table, and I'm going to take all the code that I had from the global alignment table, and I'm just going to copy it over. So we already have a global alignment table that does all of this stuff. And I'm going to take all of that code. I'm going to go to the local alignment part side of this, and I'm going to copy it in, because our initialization is going to stay the same. The number of rows and columns is going to be the exact same. We'll set a bunch of default 0 values for the table. Nothing wrong with that. There's kind of only one real place that's going to change. First off, if you're entering an element in the first row or column, well, remember, you could do that with a gap, or you could just start there for free by jumping from the source. So you would always take that option. So really what we're doing is we're replacing this with a 0. We would never want to start an alignment with a gap. That doesn't make sense, because we're just accumulating negative penalties for no reason. So notice they're already equal to 0. So all of this code is now no longer necessary. So the first row and column values are 0 already, which is good. Then we range over the interior and apply the recurrence relation. So notice we have an up, a left, and a diag. All that is good. Same thing as global alignment, except add one little old term. And in terms of making the scoring table, the problem is now finished. You'll notice that there's a little bit more. So if I'm interested in kind of the best scoring local alignment, I would just take the maximum value in this table. A little bit different from just taking the bottom right, but not substantively different. However, this problem asks us not just to find the best scoring multiple alignment, it also asks us to find the substrings themselves that produce that. So this is nice, and we could form an alignment of these strings, but this tells me what are the substrings that actually produce the best alignment. And so it's saying, the similarities here are here and also here. So with respect to PAM 250, those are the regions of maximum similarity in those strings. This is like the foundation of a huge amount of study in computational biology and bioinformatics. For example, the tool BLAST is based inherently off of this local alignment algorithm. If you've ever used BLAST, one of the most cited scientific papers of all time, it's been in use for decades as a software tool for analyzing, like, I have a fragment of DNA or protein I'm interested in, where does it come from? Well, the acronym BLAST, the LA in BLAST, stands for local alignment. So it is inherently tied into a lot of different analyses that we perform in computational biology with respect to string algorithms. And we can implement it without making a huge change in what we have. We already have the dynamic programming table for local alignment. It's just global alignment essentially with this, and where the first row and column are all 0s. The local alignment function that I want to write is going to take 2 strings, a scoring matrix, and my gap penalty. And then, well, it's going to produce 3 things. It's going to have the best score of any local alignment as a float. And then it's going to have the 2 strings that I care about. I could do a little better than this, really. I probably could indicate the positions, starting and ending positions in the strings. That would be a little more precise. And I even could produce the alignment of itself of those 2 strings. So this function could be a little bit stronger, frankly. And really, when you look at our bioinformatics algorithms text, we've got an interactive text where you can solve, a bunch of coding challenges in it. They're probably framed quite a bit better, so to make sure that we're actually returning everything that we would want to return. But for now, this is okay. Like, we're going to solve the problem still. I just won't have the alignment that we care about. So what we're going to do is just return the score and then the 2 substrings of the strings that I care about. The first thing I'll do is make the table. So I'll make the table by saying make the local alignment table. And I'm going to take ST matrix and gap penalty. And then we're going to say num rows is equal to the length of S plus 1. Num calls is equal to the length of T plus 1. And then the first thing we might want to do is actually find the max. So this first element of the tuple is going to be the score of the best local alignment that we can find. So find the max. And I'll say start it at 0. Start the best row at 0. Start the best call at 0. Okay, so the best we could possibly do is just to take no alignment, and then that's going to have a score of 0. So that's where this starts. You know, this is telling me here's where to end the local alignment, in other words. So once I've got that, I'm going to say, okay, range over all of your rows, range over all of your columns, and if it's the case that the value at this particular position in our matrix is bigger than the best score that you've encountered thus far, you know, this is my ability to take the max over all values in the scoring table. If that's the case, then we want to set the best score that we have found equal to that current known best. And we want to update the best row to be equal to the row. And we want to update the best call to be equal to the call. So at this point in time, we know that eventually we're going to return the best score, but we're going to return two other things. And those two other things are the two strings that we're actually going to align in this best local alignment. So let's trace back from the maximum cell, and that's at best row, best call, until you hit a score equal to 0. So to do that, I'll say, let's create two indices, R and C. R is going to start out being equal to best row. C is going to start out being equal to best call. And I'll say, we're going to actually start decreasing R and C. This is similar to what we did when we backtracked to form an edit alignment. But I'll say, while it's the case that R and C are both positive, and it's the case that the current cell that you're interested in is actually bigger than 0, we say, which predecessor did we come from? And we can check that. So this just allows me to know which direction to move in. So if it's the case that dp of RC is equal to dp of, double equals, dp of R minus 1C, and this is minus a gap penalty, so this says, well, we came from up. So move up. And how do I move up? Well, I just do R minus equal 1. I'm going to have an else if that says dp of RC is equal to dp of RC minus 1 minus the gap penalty. So we came from the left. And if I came from the left, I want a C minus equal to 1. And then we have an else, and this is the diagonal case. So I'm going to do R minus equal to 1, and I'll do C minus equal to 1. Once I reach this point, I know that the two strings range between indices R and best row in S, and C and best row, best call in T. So the substring of S that I care about is the substring that starts at R and goes up to, but not including best row. And the substring of T that I'm interested in is the substring that starts at C and goes up to best call. So now I know what I need to return along with the best score. I'm going to return the S substring and the T substring. All right. Let's see if we can get the answer here. That's good. Looks like what we had before. So I'll get rid of this multi-line comment for our parsing. We'll grab a data set from the platform. And we'll run it one more time and get an answer. So that answer is going to get pretty big. We'll go into output.txt though. So we get score 1249, and for the strings that we had, it says the best, local alignment is going to be these two. Again, the nice thing about having a matrix of scores, a scoring matrix, couldn't think of the term. The nice thing about having a scoring matrix like Blossom, like PAM, is that you get all these different values assigned to different possible substitutions. And so we can be pretty comfortable that, this is a lot of similarity, 1249. That's the maximum similarity subregion. You can see some of this. I mean, it's tough because you see QL and then you see AY and QH, and you say, well, some of these are starting to, not match exactly. But that's the whole point of why protein alignments with scoring matrices are good. Because just because you see a mismatch, and often you'll see a lot of mismatches, doesn't mean that you wind up with different structures or different proteins at the end of the day. You might be changing one amino acid for something that's very similar. And so you wind up with the same protein structure. It's what makes the language of proteins and understanding it so complicated to begin with. That's, of course, subject for another day. I probably should solve this problem first before I time out. And we're in good shape. If you have questions, let me know. We're going to do SMGB next. And SMGB is the semi-global alignment. It's another alignment variant. Probably our longest question of today. So I'll go through it quickly. Then we're going to have a problem that's going to seem very, very hard at the end. And it's like a classic Rosalind question that it seems hard, but it's actually not. So we've got a long one and a short one to finish. Okay. All right. SMGB is semi-global alignment. And we've covered global alignment, which is like comparing an entire gene against an entire gene. We've covered local alignment, which is like a subregion of a gene against a subregion of a gene. But there's a natural question, which is, what do we do if we want to find a region from one gene and align it against all of another gene? A classic, or another string, a classic example of this would be like, I have an existing genome and I've done a lot of work and figured out exactly where the genes are in that genome. And then I have a related organism that gets its genome sequenced. So it's just a raw string of ACs, Gs, and Ts. And I want to say, well, how do I annotate that genome to figure out where the genes are without having to perform a bunch of experiments? One of the things that you might do is to take the existing annotation, so the related organisms labeled genes, and go through and for each one, try and align them against the new genome. But the problem is, I don't want to align this thing against the whole genome because it will probably just spread out the matches. I would like to align it against a region of the genome. So it should be against a substring. But then the issue becomes, well, it's all of this against a substring of the longer genome. So local alignment doesn't really apply. What does apply is this notion of semi-global alignment. And it's an alignment in which you kind of ignore any of the gaps that you see on the very ends. So it's as if you have a free taxi ride down here and a free taxi ride down from any element in the final column. So you get free rides in the first column and the final column. But the way that this problem is framed, sometimes you're assuming that one string is like shorter than the other. So in the case of the genome annotation that I talked about, you have a gene that's very short compared to the length of this long genome. And so we're going to use all of it against a small region of the other genome. What semi-global alignment says, though, is, well, we're also going to allow it to be the case that I could start anywhere here and end anywhere in the final row. So we're essentially solving a big alignment question that's trying to say, over all the ways of starting the alignment for free, whether you go down or to the right, and over all the ways of ending the alignment for free, whether you go down in the final column or right in the final row, if those rides are free, meaning they have an edge weight of 0, what winds up giving you the maximum scoring alignment at the end? So in this case, what this particular question says is, notice this string is longer than this string. And so we're essentially like fitting all of this string to this longer string. So at the end of the day, we're really solving that question of having a short region and aligning it against a longer region. And you say, well, yeah, but the alignment that we get is really long. However, notice we're not charging any of these gaps and we're not charging any of these gaps. So it's really just for ease of use to the reader that, we're not actually charging for these. And so what we're really saying is that this string aligns well against this region of this longer string. That would be perfect for the case of annotation, because it would say we took this known gene and we've identified the region within this longer genome where it's very similar. So semi-global alignment is a great application of this when it goes only in one direction. So like we know we're using the shorter string against the longer string, it's often called fitting alignment, because we're fitting all of a string against its appropriate place within this longer string. And we're going to use this idea of the free taxi ride edges into any row, into any element in the first row or any element in the first column. And then the alignment could end anywhere in the final row or column. So as we've seen before, I'm going to build the table first. And so we're going to have a bunch of initialization. So initialization is easy stuff. And we're going to say num rows is equal to length of s plus 1. Num calls length of t plus 1. dp is our table. It's a list of lists of floats. I can type list of floats. Okay, I'm going to start off empty. Then we're going to say for I in range of num rows. The current row is going to be equal to a list of floats equal to 0.0 times num calls. And then I'll dp dot append it. The first row and column are 0 because there are free rides to all these nodes. Good. So that means they're just 0. And now we can range over the interior. So it's similar to local alignment for this reason, But it's different from local alignment because we no longer have free rides like in local. So this is the part of the code that will be similar to local. This is the part that's similar to global. And in fact, I probably could just grab this from global. Although for this particular question, what we did was we don't have a scoring table. We just have a match score, a mismatch penalty, and a gap penalty. So we're assuming that mismatches always get this penalty and that gaps always get this penalty. And we'll see that in other problems too. So it's kind of like a simpler version of a scoring table where we're not treating like a W against an A as different from a W against a C. That's just going to be one mismatch score. But we could easily change this in that way if we wanted to. We just need to add the scoring matrix as our input instead. It's not what this problem calls for, so I can't exactly copy over, but what we're going to do is very, very similar. So we're going to say for row in range over all of the rows starting at 1, for call in range over all of the rows starting at 1. We'll have up is equal to what happens when we look up. So we're at row minus 1 call, and then we subtract our gap penalty. Left is going to be what happens when we look one column over, and then we subtract our gap penalty. Diag is going to depend. So we're going to say if S of row minus 1 is equal to T of call minus 1, then I'll say diag is equal to take dp of our row minus 1, call minus 1, and we're going to add the match reward. Else, diag is going to be the same element, but this time we're going to subtract our mismatch penalty. Then at the end of this process, I can set the value of dp row call as equal to the max of those three things. So we're going to have the max of up, left, and diag. And then we're at the end of our function, so we're going to return that dynamic programming table. So computing the table itself is straightforward. I will say we've not handled the free taxi rides to the end yet. So we've handled all the ones to start because the first row and the first column are all going to have 0 values. But we haven't actually said how is it that we handle the fact that we could come from anywhere in the final column or anywhere in the final row. And what I will do then is to say over all of the values that I have set now, which one is the biggest? Because if the final element is 17, but this is 470, well, I want to jump down for free. So I would take whatever over the entire final column and the entire final row in my table achieves the maximum. But I'm going to do that in the semi-global alignment function. So I'm going to take S and T and my match, mismatch, and gap, and I'm going to produce the best score and then the two aligned strings. That will be very appropriate because here's where I'm going to have the alignment of both the strings, which will be really good. So now we're really getting to the point where we're doing real alignment questions. And first, let's create the table. So we're going to say dp is equal to semi-global alignment table. And it needs to take in everything it needs, which is the whole thing. ST, match, mismatch, penalty, and gap. And I'll say the number of rows is equal to the length of S plus 1, and number of calls is equal to the length of T plus 1, so we already know that. The best score is in the final row or the final call, so we need to find it. And if we want to find it, I'll say, well, the best score. Let's start it off as the bottom right element. So I'll say num calls minus 1. Num rows minus 1, and num calls minus 1. And the best row is num rows minus 1, and the best call is num calls minus 1. So we're going to find it starting with the bottom right element and working up and to the left. Okay. I should say up or to the left. So we're going to stay in the final column or we're going to stay in the final row. So check the last column for any improvement. And if we're in the final column, I can say, let's range over all of the rows. And then if it's the case that the DP of row num calls -1, so this is the final column index, good. And if that beats my current known best score, then I'm going to update. So I'll say best score is equal to whatever that is, DP of row num calls -1. And I'll say best row is equal to that row index, and best call is equal to, well, the current column index, which has to be num calls -1. And then I'll check the last row too. So if anybody in the last row beats that value, then I'll be good. So I'll say for call and range over the num calls. And I'll say, is it the case that DP of, now it's num rows -1, because I'm in the final row, but the column index is changing. Is that ever better than the best score that I've encountered? If so, the best score is equal to whatever that value is, num rows -1, and call. And the best row would be the row index that I'm at, which is num rows -1, because I'm in the final row. The best call would be the column index that I'm ranging over. And at this point, I know that best score is optimal, and best row, best call is where I want to backtrack from to form the meat of the alignment. Okay. So at the end of this process, I know then that I'm going to return best score and something 1 and something 2. Okay. And those something 1 and something 2 are the two rows of my alignment. So I haven't formed those yet, but what I will do is, we need to build our alignment strings. And so to do that, I'm going to say S-aligned is a list of strings. It starts off as empty. And T-aligned is a list of strings that starts off as empty. And way down here, eventually what I want to return is a join of them. So this is our classic Python trick to prevent like a bunch of unwanted slow string concatenations. I'm going to join a bunch of strings together at the end with this method join. And if we call that method on an empty string, it's just going to concatenate everything together, but it's going to do so with one single step. All right, now, anyone past the best row or column is just a gap, which will be free, but we need to add it to the S-aligned or T-aligned, because remember, when we look at the platform, what's asked for is really an alignment that uses every single symbol. But this would be the case, like where in this particular case, these are indexing the columns in the way that we think about it. So if this is indexing the columns, we're in the final column at this point in time, which is good, but we're starting our alignment a number of rows above. So this is not charging this as a gap, which means we're jumping up to this position that jumps over all these symbols, but I still need to add them to all these symbols with gap symbols to the alignment, just so that it's presented to the user. And so to do that, what I want to do is range over starting at num rows -1, so starting at the end, going up to the best row that I found, and I'm going to do -1 as my step size because I'm decreasing by 1 each time. Then I'm going to say to S, in S, so this is the first case, is if the alignment doesn't end in the final row. So this would be moving up and making sure that we keep appending. So S is going to get the current symbol that we care about in S. So this would be S of k minus 1. That's adding those extra symbols of the first string. And T aligned is going to just get a bunch of gap symbols. And that's all we have to do. The second case is if the alignment doesn't end in the final column. So I'll have another for k in range. It's going to have a -1 at the end. It's going to start at numCalls -1, and it's going to go back to best call. And as I do that, in this case, S is going to have a gap symbol associated with it, and T is going to get the corresponding symbol of T. Now, once we've done all this, now we trace back through the interior until, well, you hit the first row or column. As soon as you hit that, then you can jump back. So I'm going to have two new parameters, R equal best row and C equal best call. And they're going to change each time, as we've seen in other problems. R and C are going to keep track of where we are. So I don't want to change best row and best call. There's no reason to do that. But I'm going to allow R and C to update by being subtracted each time as we go through. And so I'll say while R and C are both positive, so while we're in the interior, now we do the same old thing to say check where I came from. Okay, so if it's the case that dp of RC is equal to above me, so one previous row, same column. So this is a vertical edge and move up. What do we mean by move up? Well, we would say S aligned dot append. I'm using a symbol of S because I'm moving up and it's indexing the rows. So we'll say S of R minus 1. And T aligned just gets a gap symbol because I'm moving up. And if I'm moving up, then I want to subtract 1 from R. Forgot briefly that Python doesn't have R minus minus. The other case would be, well, if when we check dp of RC, it's equal to dp of RC minus 1 minus gap. Need to call this gap penalty. And in that particular case, this is a horizontal edge. So move left. We know we're going to have a C minus equal to 1. But the case for S and T gets switched. So we see S align dot append is now going to get a gap symbol. And T aligned dot append is now going to get T of C minus 1. And then the else case is, well, move diagonally. So get one symbol from each and subtract 1 from both R and C. So at the end of the day, I'm going to have this line and I'm going to have this line, but I'm moving diagonally, so I'm going to pick a symbol from both of them. And I'll get this symbol here. So I'm just copying stuff so I know that I don't make any errors there. And at this point in time, you know, the meat of the alignment has been reconstructed, which is good. But if we go back and we look at what the platform asks for, we're not quite finished, because at this point in time, we've gotten to essentially this point. So we've jumped backwards, but now we're no longer in the interior. Where we are is, well, we still have symbols left from the first string. So if we look back at our figure, we're in this exact same consideration. We're in the first column, but we still have symbols left in that first string. And we do the same thing that we want to do that we did before when we jumped back in the final column by producing kind of additional columns that have gap symbols in them. So if we look at them, what we want to do is, you know, now it's just a matter of adding any free gaps that remain, because this was our like free ride back to the source. So we'll say while it's the case that r is greater than 0, this means that there's still some rows. So we're need to get rid of all of the symbols of s. So we'll say s aligned dot append s of r minus 1. And while, I guess I should just say t aligned dot append a gap symbol, and I should make sure that I r minus equal to 1. And then while c is greater than 0, we're going to get rid of t. And you're only going to have one of those two things happen. So one of these things might happen, but the other one won't. So we'll say s aligned dot append. Now the case is opposite. So we're going to have a gap symbol from s. We're going to have the current symbol from t, which is t of c minus 1. And c is going to get minus equal by 1. And now all this is good. One tiny little issue is that the alignments are backwards. So I could try this. Let's see what happens. Python 3 SMGB.py. And so for this particular thing, you'll see the alignments are backwards. CAG, CG, TGG. The same thing here. So in this case, that's the same data set we had. Okay. I hope this is right, because we do have one deletion there, and we also have one, so we have one mismatch. So what this is assuming is that matching symbols cost 1, substitutions count 1, and the gap penalty is 1 also. So gaps and mismatches cost the same amount. So what we wound up producing was an alignment where all of the matches are here, and that's good. I guess we have a G against an A and 2 gaps instead of like 1 gap and 2 mismatches, which is what we see on the platform. The problem though is it's in the wrong orientation. And so as a result, what we need to do is to make sure that we reverse them. So we'll say s-aligned dot reverse and t-aligned dot reverse. And now when we switch this, get a different answer. Pretty good. One point is there's actually a little bit of bias in an algorithm like this, because the order in which you consider these statements could actually produce slightly different results. So as I move backwards, this would say to try and move horizontally first instead of vertically first, and that order of backtracking could produce different results when you see it. And we also could check the diagonal case first, and that could produce different results too. That's a minor point. At the end of the day, I feel like we've got something that appears to be working. It just gives a slightly different alignment than what the platform has, but I think the score is going to be the same. This is another point of why you vary the scores and make sure that you use things like Blossom or PAM so that you wind up with only one solution at the end of the day, because you have that richer data set. But I've solved this question for it. So we can download a data set and place it here. We're going to call it dataset.txt. Didn't do my cleanup. Okay, let's try that again. Dataset.txt. And comment out, uncomment out the parsing stuff. So that now this will produce an answer for us. If you look at dataset.txt, look, we got 2 very long strings. Pretty neat. When we run it, it's probably going to take a little bit of time. it got printed in the console, but also here's our alignment. So this is the first string. It's quite long. And we have our second string as well. It shows you that, you know, what we really need from this point forward is something like an alignment viewer. These strings are getting so long, in order to line them up, we need like a little software to do that. I got the wrong answer. Oh, good. Good. That's good. Well, I can try it again in 53 seconds. Yeah, I'm worried. You know, I know I've got the wrong answer here because I was getting 2 indels and 1 mismatch. But the platform here says you get 1 indel and 1 mismatch. So you're only losing 2, and I was losing 3. So we're really close. But that's not quite good. Not quite good because comment that back out and run it again. This is some similarity, CAGC, but we got a mismatch here, deletion, and another deletion. So for whatever reason, it's not quite winning. It seems like it's trying to force it all the way to the end, right? Like it correctly figures out that this is the end of the alignment, this G against a G. And that's good. It's really this move. I guess these two don't really matter. But it should be a T and then a G so that it can start picking up this C again. Really not sure. So my sense is I probably got something at the point where it messes up. So we feel like these are right. This looks good. Good too. Could also, I guess, have set the table incorrectly. Click here. Looks pretty good. I'm open for suggestions. We can always crowdsource this. So I don't have to get deep into testing here. This should match this, which matches this. I mean, we're getting a valid alignment. Go up here and we see ST mismatch gap. It's 111. Print this. I don't know what I was thinking here. Hmm. 1, 2, 3. 1, 2. Here's our max. So that's our max, and we should trace back from there. If we look at our correct solution. Copy it in. So that 4 sits at this particular point where we've aligned, this end against this big gap. And we're going to have a match and a match. Our solution is getting printed as this. Space so they line up a little bit. So from here we go backward, and that's good. So I get this to this particular point. The ideal solution really should continue going diagonally. Right, so I guess it could have come from above. So we've gone this way, 3.0. Yeah, because it's a T against the gap, so we've gone up there. And we go a T against a T, so we've gone here. Gone a C against the gap, so we went here. G against an A is 4. And when that's right, at this point in time, we just have 4 more matches. Just 2. Seems like it's making the right decisions. Which is not good because this is provably worse. Get 1, 2, 3, 4, 3, 2, 3, 2, 3, 4. Okay, so that's a score of 4. 1, 2, 3, 2, 3, 2, 3, 4. So ours does actually solve the question at hand for this data set. So it's working on the small sample. This is a classic Rosalind thing. This is why we moved beyond autograders like this, because we have a small data set where our code actually is working. It's one longer. It's got one extra match, so that's why I was a little initially confused, but it appears to be actually like there's nothing wrong with this alignment. And maybe I truncated or something. But at least have a lot more confidence in what we did. And let's try this one more time. I've got a really bad feeling about something. And that's that it might be just assuming that this is an integer. So I've written a very general version of this, but Rosalind, the platform, just all it expects is this: add 1 every time you see a match, subtract 1 every time you see a mismatch or an indel. Like, could it be that? Could it be this little parser that if that's a 0.0, it's not going to like it? No. Okay. It's so mean. It's just telling me wrong. Much has changed in education. I copied the full thing. Ugh. Yuck. Yuck, yuck, yuck. Oh no. Let's see how that could be causing any issue. It appears to be the same. That would definitely be wrong. I think I forgot to add the else if back. I don't think this is going to solve anything. I'm going to give this probably one more go. So let's try this. The platform will give us one more data set. It would definitely produce a very bad error. And it's an alignment, and it's giving us a good score. So any issue that we have, it's going to be so minor. I can't believe that's all it was. And I think even today I was talking about if versus else if and how important it is to know the difference. And then what did I do? I was just showing you, hey, the alignment will change on our sample. And I'll just move this if here and this if here. And I forgot to make this an else if. So that didn't arise in the sample. I mean, my word, what an awful bug to try and catch. But, so the sample doesn't have this case that it happens to be the case that this is true and this is true. And so if that's the case, then you're making 2 moves when you should have made 1. And so that's where we get that issue from. But at the end of the day, hey, we solved the problem correctly. I was just curious to see if this changed our solution. I don't think it would have changed the sample. It's up here somewhere. Yeah, it didn't change the sample that we got, but you could come up with the diagonal one first and you would get an answer. All right. Completely quiet chat through the whole thing, just watching me fail. That's okay. I'm not angry. All right. We got one question more to go today. And that's just going to be a much easier question. MGAP. Not an easier question to understand. It's a challenging question to understand. But it's a short question. All right. MGAP is maximizing the gap symbols of an optimal alignment. And the idea of this question is we change the parameters, we're going to produce very different behavior in terms of the alignments that we obtain. We appreciate this, I think, already from the perspective that we've solved different alignment questions. But there's a very intuitive idea here, which is that, well, what happens if you make the gap penalty really big? Instead of a gap penalty of 5, you make it 500. What would happen is you're just going to very rarely see gaps. Now, if the two strings have different lengths, you're going to have some gaps, but I think you get my idea that if you make the gap penalty equal to 500, well, for this string and this string is one symbol longer, so you're only going to have one gap, and that's because the gap penalty was so high. Similarly, if we make the gap penalty tiny, then we're going to have tons of gap penalties. And by tiny, I mean compared to what the cost of a mismatch is. So you reach a point, like imagine that you have an alignment and you matched A against a C. You reach a point where if the gap penalty is small enough, you wouldn't do an A against a C. You would just do an A against a gap and a gap against a C. That doesn't necessarily make the most sense. And for that reason, gap penalties usually are higher than your mismatch penalties, or around the same. So you're not going to have that particular concern. But it leads to a question, which is, well, as we change these parameters, different things happen to the alignments. And one very, I think, natural question, is a starting question that we might ask is, what's the most number of gaps or the fewest number of gaps that we could ever get as we change these parameters and we get the best alignment? What's the maximum or the minimum that the number of gaps could ever be? The minimum on the number of gaps is really easy. It's the difference between the length of the two strings. So as I said, if the gap penalty becomes egregiously high, well, you just never take gaps. And so if you have a string of length 6 aligned against a string of length 7, you're only going to have one gap to make sure that the alignment actually has the appropriate length. And that's all you're going to have. But what about on the other end of the spectrum, where the gap penalty is tiny compared to the charge that you're assigning to a mismatch, which I think we're saying here is just, we're calling it D, and G is our gap penalty. So if this is much smaller than the charge for a mismatch, that's going to seemingly create a lot of gaps. And can we figure out what that needs to be? If I give you two strings, can you tell me the maximum number of gap symbols that could ever appear for some choice of parameters? And our insight here is, well, I'll say, our insight is that to make many gaps, gap penalty should be functionally 0. Like it might be 0.000000001. You can make it so close to 0 that it's essentially 0. And, in this case, we would never see something like x dot 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 a dot 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 and then aligned against dot 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 c dot dot dot. We would never see a mismatch. Instead, you'd see gaps. So you'd see dot 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 a dash dot dot dot, and you'd see dot 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 dash c dot dot dot. So you would never actually produce a mismatch. You would get two gaps for the price much less than the price of one mismatch. So this is why this would be suboptimal. But then now that we see this, we'd say, well, can we see what the maximum number of gaps is actually going to be? And I would say, well, to maximize the number of gaps, we could do this for all mismatches. So you could just perform an alignment that's optimal, that just replaces all of your mismatches with these two gaps. Remember, it's an optimal alignment. So you can't just do all of the symbols of one string against gaps and all of the symbols of the other string against the gaps. It still has to maximize the alignment score for these parameters. And so that means that it accumulates as many matches as possible. Imagine a circumstance where the mismatch score is something like 10. The gap penalty is essentially 0. Well, an optimal alignment is just going to maximize the number of matches. And so we know how to solve that. That problem is just LCS. So you're going to have two types of columns. You're going to have match columns and you're going to have gap columns in your alignment. So if we think about this and we think about, well, we've got S equal AACGTA, and we have T equal to this string, we can actually easily see for this example how this is going to work. So A against an A is fine. What is the LCS here? I think we can see that it's an A followed by another A followed by a C followed by a TA. So it's AACTA. So the G is kind of hanging out here. And this C is going to hang out, so we'll say it's that. And in this particular case, you see we've lined up the A against the C. This G against the C is bad, so I'm going to go G dash, and I'm going to go dash C. And that gives us the answer. So if you look at this, you might say, well, how is it that I would know the number of gaps that I have? Well, you have the length of the string S, which is AACGTA. So you have AACGTA. And you also have the length of the LCS. So the LCS is 1. We can see wherever you see lined up symbols, 1, 2, 3, 4, 5. And the string itself is AACGTA. So 5 of those 6 symbols from S are used as match columns. The 6th one is not. It's this particular case that gets aligned against a gap. We know it's not going to get aligned against a mismatch. So, in other words, the number of gaps in the bottom row is the length of S minus the length of the LCS. So in that case, it's 6 minus 5, which is 1. Similarly, the number of gaps in the top row is the length of T minus the length of the LCS. So this has 7 symbols. 5 of them belong to the LCS. The remaining 2 have to get corresponded to some gap symbol up here. Okay, they can't be mismatches. The only other option is a gap. So this is nice because it means that the total number of gaps is the combination of those two things. It's length of S plus length of T. And then we also have a minus an LCS of ST. We have a minus an LCS of ST. And what do we do in algebra? Well, you have a subtraction twice. So it's just 2 times that length of LCS. And that gives us a nice closed formula. So we're actually done. It's just this particular formula. And the only reason we're done is because we already solved LCS. So I can use my LCS code that we've already written and just get to length of S plus length of T minus 2 times that length of the LCS. And so here I'll say, make our LCS score matrix for the 2 strings. That's a problem that we solved a long time ago in LCSQ. And the length of the LCS is the bottom right corner of this table. As is often the case with alignment questions, the best score is your bottom right element. So the LCS length is, check that table, row index is length of S, column index is length of T, and I want to return length of S plus length of T minus 2 times LCS length, and that's going to solve the problem. So when we call this on our problem here, we get an answer of 3. So far, so good. I'll uncomment out the parsing part of our code. Need to get a data set. I'll put that data set in my folder. Call it dataset.txt. We're going to run it one more time. And it's taking a long time only because it's got to form the LCS table. So when we had LCSQ, it's building this LCS scoring matrix based off of the LCS recurrence relation. And the LCS recurrence relation is check these 3 predecessors. If you have a match, then you add 1 to the diagonal, but you have up, left, and diag. They're not getting any edge weights. There's only one case we have an edge weight, and that's if you have a match. So it's a simple table, but it solves longest common subsequence. And in the meantime, we have that our answer here for the most number of gaps in any optimal alignment of these 2 strings that we have in our data set is 6,468. So 2 long strings, we can solve this, I think, pretty sophisticated question really easily. And see if we're right. We got the wrong answer. Okay, of course we do. Of course we do. I don't have the wrong answer on this. I mean, this is a 2-liner. This is a 2-liner. I'm just going to make another attempt. You know, the definition of insanity is doing the same thing and expecting a different outcome. And I'm like, did I not update the data set or something? Maybe that's it, because it's a formula, you know? All right, I guess I had the wrong data set. I don't think I had the wrong formula, so it's all good. Special thanks to Thomas Wienar for that question from a long time ago. It's a good one. It really kind of gets to your understanding of how alignments change. All right, is alignment done? No, alignment's never done. People are still out there writing aligners these days to optimize them and so forth. But it's definitely, we're done with what we're going to cover today. So join us in a future time for some more alignment problems, where we're going to get into the weeds of stuff like affine alignment and really kind of get a final alignment algorithm that's going to satisfy us to align 2 genes or whatever it is that we want. So that's going to be really good. We've got more stuff as well, more evolutionary tree construction, but we're starting to see the finish line on our Rosalind problem. So if we look at our list view, we're seeing more green than anything else. We're starting to solve questions like only 301 people have solved that semi-global alignment question. So we do have some problems left. We've got some more genetic stuff. We've got some proteomics questions to solve. We've got more string algorithms type stuff. But all that's going to be the subject of another time. I'll plan on seeing you then. And until then, happy coding.